Well, let's start our class today. First of all, we need to talk about circles. We have some other facts about circles. Then we move to the areas of plane figures. And then we begin to talk about solid geometry. So, circles. We have some more properties. Well, the next property is that if we have a circle and we have two parallel chords in this circle, AB, CD, and we know that AB is parallel to CD, we can be sure that these two arcs intercepted by these two chords are equal. Well, if we have two equal arcs, we can say that we have two congruent central angles or inner angles. That's it. Well, and some facts about lengths of different line segments in circles and outside circles. If we have two intercepted chords, AB and CD, they can be perpendicular, maybe they are not perpendicular, doesn't matter. If the point of intersection is E, for example, we can say that CE times ED is EB times AE. Then if we have a tangent line, two tangent line, and they intersect in a point outside the circle, let it be AB and this is C, we can say that AB is equal to BC. So two equal line segments. Then if we have two secants, let it be ABC, and the points of intersection with the circle are DE, for instance, we can say that DB times AB is equal to BE times BC. So two chords, two tangent lines, two secants, and finally a tangent line and a secant. Again, we have a circle, a secant, a tangent line, and we know that they intersect in a point outside the circle. ABCD. We know that BC squared is BD times AB. So we can say that BC, a segment of a tangent line, is the mean proportion of a line segment of a secant outside a circle and the whole line segment of a secant. The whole line segment of a secant. Okay, so I think that we discussed all properties of circles. You need to solve the homework, and we can move to the next topic, the areas of plane figures. What is it? First of all, we need to introduce a new concept. It is a square unit. It is a square, and a side of this square is 1. So it is a square unit. And if we are talking about an area of a plane figures, we say that an area is a number of square units inside this plane figure. The simplest case is when we are talking about a square. Let the side of this square be A, and the area of this square is A squared. If we have a rectangular, the sides are A and B. The area is a product of these two sides, and A and B. The products of two sides having the same vertex. Well, next case is a parallelogram. AB equal. Here we need to drop a perpendicular from a vertex to the opposite side. So we can say that this is an altitude of this parallelogram, and the area of a parallelogram is H times B. So the length of this perpendicular, the length of this altitude times the length of the corresponding side of the parallelogram. Then trapezoid two sides are parallel to bases A and B. And also we can drop a perpendicular, so we can say that let's draw an altitude in this trapezoid. And an area of this trapezoid will be this altitude times a half of sum of two bases. So A plus B over 2. And if you remember, if we draw a midline in a trapezoid, the length of this midline will be exactly A plus B over 2. So we can say that an area of a trapezoid is an altitude times midline, the length of midline. Then let's talk about a particular case of a parallelogram. It's a rhombus. It's a rhombus. Of course, we can use the formula for parallelograms because, as you remember, a rhombus is a parallelogram. But we can use the fact that two diagonals of a rhombus are perpendicular. So we can say that an area of a rhombus is if D1 and D2 are two diagonals of our rhombus. Let it be D1 and D2. So an area of a rhombus is D1 times D2 over 2. And again, a square is a particular case of a rhombus, so we can use the formula, this formula for a square. Okay. Okay, we have discussed all quadrilaterals. But also, we can introduce some formulas for other plane figures. For example, we can talk about so-called irregular polygons. They can have any number of sides and angles, They are regular if all the sides are congruent and all the angles are congruent. So, for example, we have A1, so on AN, and we know that A1, A2 is equal to, so on, AN minus 1, and AN, A1, and all the angles are also congruent. For example, we can talk about a right triangle, a square, regular pentagons, and so on. So any number of sides and angles. And if we are talking about such figures, we can say that an area of this figure is an apothem. I'll tell you about it, times perimeter over 2. What is an apothem? So let's talk, for example, about regular hexagon, right? So we have 6 sides and 6 angles. This is the center of this hexagon. This is a point of intersection of 2 diagonals, for example, or we can say that this is a point of intersection, or this is the center of inscribed circle or circumscribed circle, doesn't matter. So this is the center of this figure. Let's drop a perpendicular to one side. Our hexagon is irregular, so we know that this point, the point of this intersection, will be a midpoint of this side. And this is L. And if we want to calculate the area of this figure, we need to take this L and multiply it by perimeter of this figure over 2. A perimeter is a sum of all sides of a figure. Okay, and finally, a circle. It is PR squared. Here R is the radius of our circle. Okay. So about areas of different figures, of different plane figures. Well, and now we are ready to move to the solid geometry. Well, we can consider solid geometry as an extension of a plane geometry. So we used to walk on a plane, but now we begin to walk in the space. So what do we have here? A solid. It is a piece of space bounded by different surfaces. These surfaces can be plane or they can be curved, doesn't matter. Wait. For example, we can consider a cylinder. Further, we will give the strict definition of this figure. Here we have 2 parallel planes, 2 bounds, and also 1 curved surface. And we have a cylinder, for example. Sometimes we have only curved surfaces bounded our figures. For example, we can consider a sphere. Sometimes we have only flat surfaces, for example, a cube. And usually when we work with all the figures, we need to know areas of surfaces, volume S, and also we need to know our plane geometry, because usually we work with all the objects in solid geometry as an objects in plane geometry. I mean, we take different cross sections, we consider different parameters of the figures in these cross sections, and then we make a conclusion about what do we need to calculate. We start with a prism. A prism is a solid bounded by two parallel planes like this. Like this. These two parallel planes, these two parallelograms are called bases. So this is a base, and this is also a base. These faces are also parallelograms. And if we're talking about prisms, we can say that a base can be any polygon. It can be a square, it can be quadrilateral, it can be pentagon, triangle, doesn't matter. So in this case, we have four sides in each base, so we can say that we have a quadrilateral prism. If we are talking about this case, we can say that this is a triangular prism because we have two triangles here. And again, our sides are parallelograms. Sometimes we have a case when we draw a perpendicular from one base to the other base, and this perpendicular is parallel to our faces. It means that in this case we are talking about a right prism. So this is a perpendicular. Let's take a point here and drop a perpendicular to the second plane. And if this AB, this perpendicular is parallel to faces, we can say that this is a right prism. Sometimes we have a case when they are not parallel. For example, like here. Well, this prism is not right prism. A particular case of a prism is a cube. It is a prism, it is a right prism with a square in a base. let it be ABCD. And we know that ABCD is a square. Also, we know that this is a right prism. So this is a cube. If we have a right prism and a base is a rectangular, we can talk about, sometimes it's called rectangular body, sometimes it is called cuboid, doesn't matter. So we have a rectangular here. Right prism. Okay, the next object is a pyramid. A pyramid is a solid. We have a polygon as a base. Let's consider, for example, a quadrilateral. And then all the edges of this figure, they meet at the same point. S. For example, on a base we can take triangle or pentagon or something else, doesn't matter. So this is a pyramid. All edges meet at the same point. And if we drop a perpendicular from this vertex to a base, and these perpendicular fall in the center of a base, we can talk that this pyramid is a right pyramid. What can we do with a pyramid? We can take a parallel plane and cut off the upper part of our pyramid. And in this case, we will have so-called frustum of a pyramid. Well, let's consider triangular pyramid. Then let's take a parallel plane. Okay, we cut the upper part of our pyramid, and this figure, which remains here, is a frustum. Of a pyramid. Okay. And now let's move to the case when one of the bounded surface is a curved surface. And we have cylinders, for example, here. We'll talk about circular cylinders. They have circles, two parallel circles. And also its cross-section of this figure is also a circle, the same circle. So in this case, we are talking about a cylinder. If we take a point here and drop a perpendicular to the other base, and if this altitude, let it be h, be parallel to a line segment line on the face, for example here, we are talking about a right cylinder, a right circular cylinder. Well, otherwise we are talking about just a cylinder. Maybe there is a slope. So again, we have two circles, we have two bases, but if we drop a perpendicular, it will not be parallel, and the foot of this perpendicular, it don't lie on the base. If we take a center here, drop a perpendicular, we'll go to the center here. Otherwise, like in this situation, it is not so. And a cone. Here we have a base and a vertex. Like this. So this is a cone. And if we drop a perpendicular from a vertex to a base, and the foot of this perpendicular will be the center of this circle, we can say that we are working with a right cylinder. Otherwise, it is not right cylinder. And as with a pyramid, we can take a plane which is parallel to the base of a cone, and we can cut the upper part of this cone by this plane, and we'll get so-called frustum of a cone. So we have a cone. We have a plane here, and this part, remaining part, is the frustum of a cone. So again, two parallel lines. And the final solid body is a sphere. You can meet in some books that a sphere is a surface of a ball, for example. Sometimes a sphere is a ball. So if we consider a ball, sometimes a sphere is just a surface of this body. Sometimes it is a surface and an inner side. So it is like we decide. So we will consider a sphere as a ball. So it can be a surface, and it can be a surface with the inner part of this ball. A sphere is a solid body such that if we take any point on its surface, here, and we find a distance to the center of this surface, of this sphere, let it be r, uppercase r, this distance will be always the same. So all the points lying on the surface of a sphere, they are equidistant from the center. From the center. And as I said before, if we have a problem in solid geometry, usually we reduce this problem to a problem in a plane geometry. So we consider different planes, we consider different projections, and so on. But we need to know such things as volumes of our solid bodies and surfaces of and areas of surfaces of this body. So we need to know how can we measure our solids. Well, we will use a table to collect all the information. The columns will be area of a surface, and the second column is a volume. And we will consider different solid bodies. So let's start with the cube. So if we know a side of a cube, we can say that area of a surface is 6 times s squared. Here s is a length of a side of a cube. So why it is so? Because a cube has 6 faces, and each face is a square, and an area of a square is s squared. Here, s is a side of this square. And if we're talking about a volume, it is s cubed. So this is our cube. S is the length of its side. Well, the next solid is a cuboid. It is also a right prism, but we have a rectangular. And let's say that this cuboid has length, width, and a thickness. Let it be A, this side is B, and this side is D. If we want to calculate an area of a surface, we need to calculate areas of all 6 rectangulars, because the bases are rectangulars and each face is a rectangular. And then we need to summarize everything. So we have 3 pairs of rectangulars. The area, for example, of this face is AC, then BC, and so on. So the final area will be 2 times AC plus AB plus BC. And if we are talking about a volume of this cuboid, it is the product of all three parameters, A, B, C. Then let's consider a prism. Okay, no, well, actually, we can say that a cube and a cuboid is are the particular case of prisms. But maybe we have not a square or not a rectangular at the base of this prism, so we need to consider this case separately. Okay. If we are talking about a right prism, we know the area of each base because we have two equal bases, so their areas are also equal. The area of a base is B. The area of a surface is 2B. And also we need to add areas of faces. And if we're talking about right prism, we can take an altitude here. It's h. And the area of each face will be h times p, times the side of this figure line on a base. And if we can calculate the perimeter of the base, we can calculate the area of a face. And it will be h times p. Here p is perimeter of a base. A perimeter is a sum of all sides of a polygon. And if we want to calculate the volume of a prism, for us it doesn't matter is the prism right or it is not. We just need to calculate the area of its base and multiply this thing by h. So we need to drop an altitude here and just find the product of these two things. That's it. Well, the next object is a pyramid. If we want to calculate an area of surfaces, we need to calculate an area of a base, and then we need to add areas of each face. And if we are talking about right pyramid, we can just calculate a perimeter of its base. Then we can drop a perpendicular on each face, and all these perpendiculars will be equal. Let it be L, so-called Apothem. And the area of a surface of such pyramid will be B. This is an area of a base times PL over 2. Here P is the perimeter of a base. Well, and if we want to find the volume of this pyramid, we don't care is this pyramid right or not. We just need to find an area of the base, let it be B. And we need to drop a perpendicular. We need to calculate the length of this altitude h, and volume is 1/3 times b times h. And from these two formulas, we can notice that if we have not two, but we have a prism and a pyramid with the same basis, the volume of this pyramid is 1/3 of the times the volume of the prism. So in one prism, we have three pyramids, three equal pyramids. Now, if we consider frustum of a pyramid, let's consider the case when we have a right frustum pyramid. For example, let it be triangular, but actually it doesn't matter. Here is a small triangle. Here the triangle is bigger. Let's take a point somewhere here and drop a perpendicular to the opposite side of the face, and let it be M, for instance. Let P be a perimeter of ABC. Let it be small p, and let uppercase P be a perimeter of A1, B1, C1 of a bigger triangle. So the area of a surface will be M over 2 times P plus P. And plus P plus, plus areas of each base. Because here we have trapezoids and we know the area of a trapezoid. So we can calculate this part, and then we need to add the areas of bases. And here we can have quadrilaterals, pentagons, and so on. So it can be triangle. Maybe it is not triangle, doesn't matter. We just need to calculate perimeters, and that's it. And a volume is the following thing. We need to find an altitude of this frustum of a pyramid. So it will be 1/3 times h. Then we need to calculate areas of each base. no, let's use the same notation, B small and capital B. So B, it is area of small base, ABC in our case, and B, this is an area of a bigger base. So the formula will be the following: 1/3 times H. Here is SO B small. Plus square root of B times B plus uppercase B. This is the formula. Well, also we need cones. We need formulas for cones. If we are talking about a right cone, let it be H, an altitude of this cone. This is the radius of the base, and this thing will be L. So the area of a surface of a cone, S, is the area of its base, and we know that the area of a circle is PR squared. So this is PR squared. And also we need to add an area of its other thing. It is 2P times L. And a volume of a cone. If we're talking about volumes, we don't care if this cone is right or not, doesn't matter. So the volume is 1/3 times PR squared and times H. Here H is an altitude of this cone, R is the radius of the base of a cone. And we have a cone and we have a frustum of a cone. Here we have small circle. Here we have big circle. Okay, our cone. If we want to calculate the area of the surface of this circle, of this frustum of a cone, sorry, we can use the following formula. Now, first of all, of course, we need to calculate the areas of bases. If R is the radius of a small circle and uppercase R is the radius of a big circle, the area here will be P small r squared. The area here is P capital R squared. And then we need to add P L R, uppercase R plus pi L small r. Here L is this thing. This is also R, drop a perpendicular, and this is side L. And if we want to calculate a volume of this V, we can use the following formula. Again, here we don't care is this figure right or not. So the volume will be the following thing. This is 1/3 times H. Here is small r squared. Here is capital R squared. And also we need to add mean proportion of R and R. Okay. Then let's consider cylinders. Again, when we are talking about an area of a surface, let's consider the case when the cylinder is right. This is an H, an altitude of this cylinder. H, let R be a radius of a cylinder. So the area of a surface is 2 area of these circles because we have 2 bases, and the area of each base is HR squared times pi. Oh, by the way, yes, here I forgot pi in this formula. Here we have, okay, 2 pi h r squared and plus, oh sorry, no, 2 pi r times r squared plus 2 h pi r. And if we want to calculate a volume of a cylinder, we use the formula that this is h times 2 pi r squared. And the final object is a sphere. If we want to define a sphere, we need just the radius of the sphere. The surface area is 4 pi r squared. Here r is the radius, and the volume is 4 over 3 pi r cubed. Well, to my mind, we have considered all solids we need in our course. Well, now I want to talk about so-called regular polyhedrons. Well, actually, a polyhedron is a figure, is a solid bounded by plane surfaces. So we sometimes we bound our solid by a curved surface, for example, a cylinder or a cone. But if we use only planes, we can talk about polyhedrons. And a case of regular polyhedrons, so this is the case when all faces are regular polygons. It means that they have equal sides and equal angles. And also in each vertex, we have the same number of edges. And it occurs that we have only 5 kinds of regular polyhedrons. The first type is tetrahedron. Tetra means 4. So we have 4 faces. And each face is a right triangle. Well, let's draw it. It is something like this. So we have, as I said before, 4 faces. Each side is a triangle with a side A. And at each vertex, we have 3 edges. Then the second case, hexahedron. Hexa means 6, so we have 6 faces, and each face is a square. So it is something like this. So at each vertex we have 3 edges in this case. Well, the third case is regular octahedron. Oxa means 8, so we have 8 faces, and each face is a triangle. I will not draw it, but you can, for example, Google it and find the picture. Then the fourth case, regular dodecahedron. Here we have 12 faces, and each face is a regular pentagon. And the final case, regular isocahedron. Twenty faces. Each face is a right triangle. So as you can see, we can use only triangles, squares, and regular pentagons to compose regular polyhedrons. Why it is so? Because, for example, if we consider hexagon, regular hexagon, we know that each angle is 120 degrees. And we consider the case, so we have 3 pentagons, 3 hexagons. They meet here. These are the common points. This angle is 120, this angle is 120, and this angle is also 120 degrees. So they together are 360 degrees, so they form a plane, and it means they cannot form a solid figure. So only triangles, hexagons, polygons, and squares can form regular polyhedrons. Okay, what else? Also, we have one very famous theorem we can use in our problems called the theorems of 3 perpendiculars. So imagine that we have a plane. And we have a perpendicular to this plane. Let it be A, it is B. And then from the foot of this perpendicular, from this point B, let's drop a perpendicular to any line on this plane. So here we have a line. Let's drop a perpendicular. Let it be BC, for example. So AB is the perpendicular to the whole plane, so we can say that AB is perpendicular to BC. And it occurs that AC is also perpendicular to this line L. So we have three perpendiculars. If AB is perpendicular to our plane L, alpha, and L lies in this plane alpha, and C lies on this line L, and BC is perpendicular to L, we can make a conclusion that AC is also perpendicular to L. Well, that's it about solid geometry, and I have just realized that I forgot to tell you about one fact from plane geometry when we consider similar figures and when we know the area of one figure. So, it's a topic similarity. We consider an example of triangles, but actually we can use this fact for any similar figures. So if triangle ABC is similar with the triangle A1, B1, C1, and we know the coefficient of this similarity, so we know the ratio of two corresponding parts of the triangle, maybe sides, maybe altitudes, maybe medians, bisectors, doesn't matter. So let's say that K is AB over A1, B1. Then we can say that we can find the ratio of two areas. So area of a triangle ABC, area of a triangle A1, B1, C1 is K squared. Okay, this is about areas, and also about so-called dihedral angles. We can meet with them when we consider two intersection planes. The first plane is here. The second is here. We know that if two planes intersect, the intersection is a line, and this is an angle. For example, we can consider it as an open book. So covers of this book, they form this angle, the dihedral angle. And if we want to measure it, we need to take a point here, drop a perpendicular to the line where they intersect. From this point, we need to drop a perpendicular from here, and this angle will be the measure of our solid angle. Well, I think that's it about school geometry. Next time, now I don't want to start the new topic. Next time we will start polynomials and monomials. We consider their properties. We will prove some theorems, because actually at our course we will prove any tiny thing. When we discussed plane geometry. There are so many theorems and so many facts, so we don't have enough time to prove everything. But from the next lecture, we will prove everything, or almost everything. So we'll talk about polynomials, monomials, different properties, theorems, and maybe we will start complex numbers. And that's it. And in a couple of weeks, to my mind, 8th of November, maybe, I don't remember exactly, you will have the first test. So you will have a test. You will have to do your homework. You will have to do a lot of things. So that's it for today. Thank you for the class. If you don't have any questions, we'll meet, I think, at our class today, practical class. So thank you.